This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
We are the paradoxical ape, bipedal, naked, large-brained, long the master of fire, tools, and language, but still trying to understand ourselves, aware that death is inevitable, yet filled with optimism. We grow up slowly. We hand down knowledge. We empathize and deceive. We shape the future from our shared understanding of the past. Carta brings together experts from diverse disciplines to exchange insights on who we are and how we got here. An exploration made possible by the generosity of humans like you.
I particularly appreciate being invited because I'm not a paleoanthropologist and I don't really study climate specifically. Instead, what I'm going to do is give you the perspective of the other animals that occupy the Earth, these small animals, large animals, and I'm going to definitely delve us into the future and ask some tough questions about our population. So I titled my talk somewhat provocatively about tipping points. And tipping points are they're situations of a state where you have a non-linear kind of system. And when you move beyond some particular point in that non-linear system, you can't go back to where you started. And I'm going to advocate that we're poised on the edge of a tipping point for planet Earth. So when some threshold is crossed, and the question is, are we about ready to cross it or have we already? The system is going to move into a new state. And the example I put up here is an egg about ready to go off the edge. Ice melting in the Arctic might be another one to think about. So mass extinctions, I've been asked before whether or not the Earth has shown tipping points. We know they happen in ponds, they happen in small ecosystems. But mass extinctions, in fact, can happen on a planetary scale. We already saw this mass extinction graphic. They're labeled there, the Ordovician, Silurian, the late Devonian, the Permo-Triassic, where we lost 95% of all the species on the planet. The Triassic, Jurassic, and the KT, where we lost dinosaurs and a lot of marine reptiles. The point is that these are mass extinctions, and you'll see in every case there's a drop in diversity. This is generic marine diversity. So this is a marine record, not a terrestrial one. But the point is that when it recovers, and it takes between 5 and 10 million years for life to recover after these mass extinctions, life is completely different. We've lost those organisms that founded the diversity on the planet prior to the extinction, and they don't come back. So it reassembles. It is, in fact, a new state. So the Earth is warming rapidly. You've seen many versions of this, but I'm providing here a little bit of a perspective about from our perspective. So we're here on this graphic. All of those different colored squiggles show different scenarios depending on what models are used by IPCC. We will be here. Now, you've heard a lot about the evolution of humans, modern humans. By the time we get to that point in 2050, we will have global planetary temperatures warmer than our species has ever experienced on its time on Earth. And if we happen to make it to 2100 and to temperatures somewhat above 4 degrees, Earth has not been as hot as that projected temperature in 14 million years. Now the perspective is, and this is one I'm giving you, mammal species don't live that long. We don't have mammal species on the planet that are 14 million years old. So the memory of this climate in the genomes of these species is gone. World population is still growing. Now, there will be 9 billion people on the planet by 2045. So 2045 here, there will be 9 billion people. And if we continue at, these are current fertility rates shown in that upper blue, current fertility rates, you can imagine, 15 million people on the planet. Unbelievable. In fact, fertility rates are slowing, but not fast enough. We would have to, instead of replacing ourselves, a male and a female, with 2 children, we would have to go down to just 0.5 children per person to follow the lower blue curve. So human population growth is the elephant in the room. It is tremendously terrifying. So even though the late Quaternary transition from the Pleistocene, the cold, arid Pleistocene, to the warmer, more wetter Holocene, is not exactly analogous and in fact very different in many ways to the kinds of climate we're experiencing today. In fact, there are 2 similar features. One, we are warming the environment as we move from the Pleistocene to the Holocene, and we're also expanding, as humans, we're colonizing the globe. So those 2 features are in fact something we share with what's happening today. So you heard a little bit about these dramatic warming and cooling events. Here's the Bowling Allarod, and then followed by an abrupt Younger Dryas, a cooling event that saw the extinction, for example, of Irish elk in Ireland as that environment cooled rapidly. And then we end up into what's called the Holocene, or really about the last 10,000 or so years of relatively constant temperatures. However, we expanded in this latter part of the Quaternary. We left Africa around 200,000 years ago. We colonized Europe and Asia. We colonized Australia somewhere between 40 and 60,000 years ago. And then we made it to the Americas last, somewhere between 13 and 35,000 years ago. Now, with our colonization of these isolated areas, we caused extinctions. This is a photo, this beautiful image is the menagerie of animals that used to roam in North America and are now no longer here. There are, gomphotheres, giant ground sloths, glyptodons, there's the giant bison, camels, which basically evolved in North America, left, colonized Asia, colonized South America, and went extinct in North America. And then horses, which again have millions of years of history in North America and went extinct and only to be recolonized by Spanish explorers. Historically, about half the world's large animals, animals larger than 44 kilograms or about 100 pounds, went extinct at this time. Incidentally, humans are about that size. So it's not just our impact that caused change in animal distributions and abundance. In fact, there are some small mammals like this bog lemming that went extinct at this Pleistocene-Holocene transition. So we know that ice covered much of Canada, and there was no place for these bog lemmings to live. Every one of those black dots you see in North America were occupied by bog lemmings during the Pleistocene. They're no longer found really in the lower 48. In fact, what they are, they're occupying this orange range up here. They are really an Arctic, circumarctic species. So they responded as you'd expect a species that likes a relatively cold environment. As the ice left, they tracked that environment northwards. But not all species responded that way. These are 2 images of 2 species that are found in a cave called Samuel Cave that I excavated several years ago in Northern California, shown by the black dot there. These two species didn't really respond north. In fact, they contracted their ranges to higher elevation, but also much wetter environments that's currently found in Samuel Cave today, which is located on the shores of Lake Shasta. So these animals, the mountain beaver, it's not confined to mountains, nor is it a beaver. It is the remnant, the last species of what was a very large group of species in the family Aplodontidae, which is a very ancient North American family of rodents, and it is the only species left in the family today. It's very primitive, and it cannot concentrate its urine. And so it has to be by running fresh water all day, all the time. And so you find them confined into very dense, old-growth Douglas fir forests along the coast and the Pacific Northwest, a very ancient lineage that is threatened by warming temperatures and dry conditions. The other animal you see is the white-footed vole. Very little is known about this animal, except the fact that it's somewhat arboreal, and it's found in deciduous trees and probably up in these old-growth Doug fir forest. Again, this animal contracted with the Doug fir forest, a wetter condition, not so much higher up in elevation. Animals today are moving poleward, just like they did in the Pleistocene. This is a range map of the current distribution in 2013. The black line is the current distribution of the armadillo. The armadillo is related to that glyptodont, that giant thing I showed you in the previous slide. It's a South American animal, and it is expanding. It made it across the Rio Grande in 1850, and it's expanding northward. It's limited by winter temperatures. So if there are 24 freeze days or more, this animal can't survive. Its young can't survive. And what's happening is, as our North American climates are warming, this animal is progressively colonizing further and further north. And so what you see, not the X's, but every other symbol on this, are instances where armadillos have advanced beyond their 2013 static range. Be interesting to know where they are after this winter. However, the thing about this that I want to point out is not just that animals respond the way you predict they would based on what we know from fossils, but the other thing is this particular animal, the armadillo, is the only mammal we know about in the world that carries leprosy. And so this is an example of these unexpected synergistic things that can in fact impact humans in ways we don't anticipate. Actually, they got leprosy from us. Leprosy evolved in Asia, most likely India, and they contracted leprosy from us probably somewhere around Louisiana. But this animal can transmit leprosy to humans as well. So similarly to what I explained to you about the mountain beaver and the white-footed vole, animals will find their proper environments. And so it's not just that they move further north. As warming conditions prevail and as drying conditions prevail, they'll also move up in elevation. So many of you might have heard about the pikas. This is one of the Asian species. There are, in fact, 28 Asian species of pikas. They're related to rabbits and hares. They're just the most wonderful thing to work with. They have this enormously interesting physiology. They have a resting body temperature of about 104 degrees, and they live really high. In the Himalayas, they live above 15,000 feet. Now, the problem so we've been studying these particular animals all along the Himalayan front in India and Nepal, and it turns out that only some of these species can tolerate the hypoxic conditions that are characteristic of that high elevation. So these particular animals, and in fact, they've shown to be moving up much more rapidly than American pikas, which have moved up around 150 meters. In the Himalayas, they've moved up at least 1,000 meters, and they're pinched, right, from above because of those hypoxic conditions, and from below from warming and also human alteration of their environment. Now, another kind of unexpected example, and again to demonstrate just what ecosystems mean in terms of how species are connected, This is the map you see on the left is a map of the distribution of, on present, the whitebark pine distribution in North America. Whitebark pine is a high elevation pine. It's the last conifer that until you get to tree line. So it's the thing that you often see as crumholts in the Rocky Mountains. It's a 5-needled pine, and it has these really, really nice calorically rich nuts in the cone. If we just look at climate models for the distribution of the whitebark pine, and you can go to 2030, 2060, and 2090, you can see by 2090 there's barely any whitebark pine left in the lower 48. Now that projection was made before we saw what happened with the mountain pine beetle. For those of you that have traveled anywhere in the Rocky Mountains, you know that in the last decade, conifer forests all the way up to tree line have been decimated. In the Yellowstone region, in some of these areas, whitebark pine are down 80%. This is a photo from one of the high elevation areas that I work in Yellowstone, and you can see a lot of standing dead trees. Now, okay, so that's because the beetle is allowed to survive over the winter. It's not killed off, it's a native beetle, but climate is definitely implicated in the expansion of this beetle. It now goes all the way up to tree line, it's not killed off, and it probably reproduces several times per year, instead of having to recolonize every year. Well, why is that? Why do I have a picture of a grizzly bear? It turns out that the number of whitebark pine cones in a tree is directly correlated with overwinter survival of adult bears and their cubs. And it's indirectly correlated with problem bears the following summer. So when there's not a lot, in some cases they may eat 40 to 50% of their fat as a result of eating these middens of cones that are mostly, again, another player in this are the Clark nutcrackers and the red squirrels here. But these grizzly bears need this to pack on the fat. And what happens is they come out of hibernation earlier and they start getting into trouble looking for food in human dwellings. So again, an unanticipated and kind of surprising but very major impact from climate change. The other thing that happens, and these are data, I'm not showing you the actual data, but during the Pleistocene-Holocene transition, there were lots of different small mammals in the Samuel Cave site in Northern California I talked about, but the animal that just took over that site is the deer mouse, Paramiscus maniculatus. And in fact, this animal has dominated the entire Holocene assemblage. So the community structure of small mammals changed. And this is not due to human hunting, this is due to the fact that there are many more disturbed environments in the Holocene. This animal has very high intrinsic rates of growth. They don't care what the environment is. They don't mind if it's just been burned. They don't mind if it's the edge of a field or if it's an old growth forest. They like disturbance. This animal is the most commonly trapped small mammal in North America. So if you lay a trap out there anywhere outside of human habitation, you're likely to catch this guy. It also tends to carry a lot of diseases. So this is a weedy species, and it thrives with human environments. And the specialist species are the ones that take a nosedive. Now, I'm sure there are some of you that are gardeners here, and they don't consider this pocket gopher as a particularly favorable friend in their garden. But in fact, these guys took a hit at the end of the Pleistocene. This is a pocket gopher. It has fur-lined cheek pouches, and it stores its seeds and digs. In fact, this is a specialist species. It is so energetically expensive to live underground. It takes between 360 and 3,400 times the energy to do this than to move the same distance above ground. This is, by any accounts, a very specialist species. So they decline. Humans are directly causing the extinction of animals. We've lost or are threatened to lose almost a quarter of our species. I just read an article that said about a third of our bird species in Europe are threatened. Most of these are from hunting. We're about ready to see the loss of elephants in the next decade or two. 1 out of every 12 elephants was killed in just the last 3 years. This is a crisis. 51% of humans, of the terrestrial land has been co-opted for human use. The only places left on this map that aren't shown in purple are deserts and tropical forests. Those are the least easily farmed land on the planet, but they're also, in some ways, especially the tropical forests, some of the most important. Everywhere else, we have made a mark. We have an extinction debt, and we will lose a lot of biodiversity in the near future. I get asked a lot, can speciation rescue biodiversity? Absolutely not. Species take between 2 and 5 million years, this is mammal species, to evolve. So we can cause them to disappear in a decade or two, but it takes millions of years to accumulate the diversity we might have lost. So how do we avoid this tipping point, this planetary tipping point? We increased energy conversion, obviously. We stall habitat loss. We increase global cooperation. This has got to be done globally. And we stabilize population growth. And finally, how do you stabilize population growth? I get asked what is the most, in my opinion, the single most important thing for us to do is to educate women globally. And the reason is because as education goes up, fertility rate goes down. The more girls that are in school, secondary school, the number of years is really important, the more fertility rates go down. And interestingly, GDP and poverty rates also go up. Human innovation is remarkable. We can see the origin of the universe. I can't believe we can see the origin of the universe, and we can see ourselves and our beautiful planet from space. Why can't we avoid the next tipping point? Thank you.